Toughness of composites. So far we have looked at composites' strength and elastic modulus. However, one of the very important property of composites is their high toughness. So in this video I will explain to you how composites get very high toughness. Let us first define toughness. Toughness in general for any material. What do we mean by toughness? Toughness is a measure of the energy absorbed per unit of the new crack area created. So whenever a material fails, and toughness is related to the failure of the materials, that means fracture of the materials. So whenever a material fails by fracture, crack grows. A crack may be present on the surface or inside the bulk of the material, and this crack will grow as fracture continues. How much energy the material will absorb for per unit of the new crack surface area. So this is the measure which we call toughness. That means a material which is tough will absorb lot of energy before it fractures or as it fractures. As the crack grows, it will continue to absorb lots of energy. So that means this material will be very tough. Now let us look at this figure. So this is a plane stress condition of a specimen. So this specimen has unit thickness and this specimen has got a crack in the center. The dimension of this crack is 2c. Sigma is the nominal stress. That means the stress we apply on this specimen. This crack has thickness which is unit thickness. So we assume that this thickness goes all the way through the material. Now when we apply the stress at the two ends, this crack will get stressed. So the stress will be also experienced at this crack. So when a stress sigma is applied in the specimen with a crack, for every incremental increase in crack length dc, so this crack is going to grow. So as it grows, it creates new length in the crack. So for every incremental increase in crack length dc, there is an increase in the new crack surface area. And with the new surface area, it will have new surface energy as well. As you know, every surface has got surface energy associated. So that means when we create new surface area, we are actually going to increase the energy of this system because new surface area means new surface energy associated. And there is a decrease in the elastic strain energy. So the surface energy will increase, but as the crack grows, there will be a decrease in the elastic strain energy. So elastic strain energy is associated with any material which has got stress in it. So whenever we apply the stress, and this stress will lead to some strain, and because of this strain, the whole material will get what is called elastic strain energy. So the material is still within the elastic range. So this energy is in the system. So when the crack grows, the elastic strain energy will reduce. That means the material will relax to some extent, but the surface area or surface energy will increase. So there is a decrease in the elastic strain energy that is stored in the crack tip. So here near the crack tip, there will be high amount of strain energy associated. When these two energies are balanced, a condition is created for the crack growth or crack to grow. So we are dealing with two energies. One energy is going to reduce as the crack grows. Another energy, surface energy, is going to increase. So as you know, every system would like to minimize the energy. So this crack will grow only if the total energy of the system is going to reduce. That means the elastic strain energy release is slightly higher than the surface energy created. So this is the situation. So a limiting situation will be when these two energies are equal. So this is the basis of why a crack will grow, because there are two energies, the elastic strain energy which is in the system and especially near the crack tip. So as the crack grows, the elastic strain energy will reduce, but as the crack grows, the new surface area will be created. Therefore, the surface energy will increase. There is a balance between these two. Now, I said that near the crack tip, there is a lot of elastic strain energy. This is because of the stress concentration. You may know that when there is a crack near the crack tip, there is a stress concentration. So, even though we are applying the stress sigma, which is called nominal stress, but actual stress as the crack at the crack tip will be much higher. And this graph shows schematically how the stress will vary in this direction. So near the crack tip, very high stress. As we go away from the crack tip, the stress will become the nominal stress. And this maximum stress near the crack tip is given by this equation. So sigma max is approximately equal to 2 sigma. Sigma is the nominal stress multiplied by C over rho to the power 1 by 2. C is half crack length and rho is the crack tip radius. So here this is the crack tip and the radius of this crack tip is rho. So you can see the sharper the crack tip, that means smaller the value of rho. So if the crack tip is very sharp, the value of rho will be small, the stress will be high. Any crack which has got very sharp crack tip will have very high stress associated with it. That means at the crack tip, the stress will be very high. So this is the reason why a brittle material tends to fracture more easily than a ductile material. Because for brittle material, the crack tip is very, very sharp, like for example glass, and this crack tip, at this crack tip, the stress is very high. Whereas for a ductile material like a soft iron, for example, at this point, when the stress increases, there will be ductile deformation. And this ductile deformation will blunt the crack. It is known as blunting of the crack because by blunting we mean the value of rho will increase and therefore the stress will come down. So for ductile material, at the crack tip, the stress is low, but for brittle material, at the crack tip, the stress is very high. And this is the reason why a brittle material is more prone to fracture compared with ductile material. Now let us get back to this energy equivalence or energy balance. So the change in total energy of the system, delta UT, is equal to US plus UE. US is the energy, the surface energy, which is increasing, and UE, which is the elastic strain energy, which is reducing. So at the necessary condition for crack growth, so just at the point when the crack might start growing, d delta UT over dc is equal to 0. So let me explain to you this energy graph and how we can decide whether an existing crack will grow or not. So for any material, a material will have cracks of different dimensions. It will have population of cracks. But whether these cracks or out of these cracks, which crack is going to grow can be decided by this energy graph. For a given stress, so whatever stress level we have in the material, so this is a nominal stress. So for a given nominal stress, we can decide which size of the crack is going to grow. So in this graph, we have on y-axis we have energy and x-axis we have got half crack size, which is C. Now let us see the different crack sizes. For zero crack size, of course, there is no energy associated with it. For a crack which has got dimension of this, for example, this size of the crack, for this crack, this red line indicates the surface energy and this green line indicates the elastic strain energy decrease. Now, since the surface energy is going to increase as the crack size increases, so we have got this line on the positive side, and this is a linear function of gamma s. So gamma s is the surface energy per unit area. The elastic strain energy is decreasing because for this crack size, if the crack is going to grow, the elastic strain energy will decrease. So therefore, there will be a total decrease in the energy of the system. So this is how it is decided. So delta UT, this blue line, is the resultant of the two. That means this minus this. Since this is linear and this is quadratic function, there will be a point when the total energy change is going to change its trend from increasing to decreasing. That means up to this crack size at the given stress, there will be increase in the energy of the system if the crack is going to grow. So that means this condition will not let the crack grow any further. So any crack of this size will not grow at this given stress. But if there is a crack which has got the critical crack size, then this crack is prone to grow, because any minor increase in the stress will lead to a spontaneous growth of the crack, because energetically it is very favorable, because at this point the total energy of the system can decrease if the crack size is going to grow. So the system will prefer to decrease the energy of the total energy of the system, so that means the crack will grow. So this is how we can decide whether the cracks present in the material are critical or not, or whether they are going to grow in a spontaneous way or not. So if the crack sizes are in this range, then for this stress, none of the crack is actually going to grow, which means that the material is quite safe. But if the crack is of critical crack size, then at the given stress, this material is prone to fracture in a spontaneous way. So by using this energy balance calculation, actually we can find out whether the crack size, that is existing crack size, whether it is critical or not at any given stress. Differential will be 0, and this we have already given as US plus UE. So US is the surface energy, and here I will tell you how we obtain this one. When the crack is growing, for example, first of all we should know that crack has got two surfaces, one above this one and one is the below. So that's why we have got 2. Then 2C. 2C is the crack length here multiplied by this dimension, which is the thickness, which is the unit. So it becomes area, and area multiplied by the surface energy, which is the energy associated with per unit surface area. So this whole thing becomes the surface energy of the crack, and the elastic strain energy is given by this one. So here again we have got 2 because there are 2 tips here, and the elastic strain energy in general is given by sigma square over 2E. So here sigma is the nominal stress. So we are not talking about the stress near the crack tip, but we are talking about the overall stress, which is called nominal stress. So sigma square over 2E is the strain energy per unit volume in any strained material, in any material which is under strain. So multiplied by the volume, we can get the energy. Now the volume is approximated as pi c square multiplied by the unit length here. The amount of volume that is strained, that is affected by this crack, is approximated as pi c square. C is the radius, and you can draw a circle of c radius and you multiply with the thickness of this specimen. So that gives the volume of the material multiplied by the strain and energy per unit volume. So total becomes the total volume. So as I have said, for unit crack width, the width of the crack we have taken as 1. So this equation is for unit crack width. Now this equation can be solved, and if you solve this equation, you get this. And from here, you can write this equation. So sigma is equal to 2 gamma s. Gamma s is the surface energy of the material, E over pi c within bracket power 1 over 2. Now sigma has been converted into sigma f to indicate that this is the fracture stress. So this is the critical stress at which the fracture will initiate. So this gamma s is a constant for a material. E is also a constant. So here we can see the relation between sigma f and c, which is the crack length. So there is a relation between the fracture stress and the crack length. So as we increase the crack length, the fracture stress is going to go down, decrease. So that means if the crack length is large, so this material is going to fracture at a lower stress. When the crack length is smaller, this is a very small crack length, then the stress at which the material is going to fail is going to increase. So this relation gives a very useful relation between the crack length and the fracture stress. Now this part of the equation can be written in this way, where 2 gamma s is written as G, and G is the toughness of the material. So this G is defined as the toughness of the material, which has units of kilojoule per meter square. So the energy per unit area. So this is how we define toughness. So toughness is a property of a material, and this property is related to the fracture of the material when in the presence of crack. Now you might have studied about Griffith criterion. So this equation is known as Griffith criterion for crack growth in brittle materials. So Griffith gave the equation, this analysis and this equation for brittle material, but this equation is also applicable for other materials which has ductility. So therefore this equation is quite general, and we can obtain toughness of any material. All we have to do is to conduct a test like this with a crack in it. This crack can also be a surface crack instead of a bulk crack. So when it is a surface crack, then you can imagine this will be only half part of this crack, because at the surface you cannot have this kind of elliptical crack. So at the surface you will have got half of the elliptical crack. So therefore the length of this crack will be given as C. So we will write only C for surface crack. We can write this equation GE to the power 1 over 2 as equal to sigma F under root pi C. So sigma F is the fracture stress for a given crack length. So that means these are critical. This is called critical crack length. That means at this crack length and this stress, the fracture will initiate. And this value of sigma F under root pi C is known as the critical stress intensity factor or fracture toughness, which is given by KIC. But in this relation, another term is introduced, which is Y. Y is a geometrical factor. So depending upon the geometry of the crack and the geometry of the specimen, the value of Y may change. This is only numerical value. Often for simplicity, we can take Y as 1. So this is a another valuable equation using which we can find out the fracture toughness of the material. So now you can see that the fracture toughness of the material is related to the toughness through this equation. And these are all for the critical crack. By critical crack, we mean that we have applied the stress enough that the crack is going to grow. It is starting to grow. So just at the point of growing, we can say that the crack is critical and the crack is growing. And at this point, these equations are valid. So this analysis I have presented for any bulk material, not necessarily composites. So what is the difference between other materials and composite materials? So let us talk about that. Now, toughness property of a composite does not follow the rule of mixtures. We have seen that strength and also modulus both can be, in some way, we can use the rule of mixture to find out the strength or modulus in some conditions. But this relation is not valid for toughness. So for example, if I say the toughness of the composite is equal to the volume fraction of the fiber multiplied by the toughness of the fiber plus volume fraction of the matrix multiplied by the toughness of the matrix, then this equation will not be valid, because for example, if we are using glass fiber, so glass fiber, we know the toughness of glass fiber is low, and if we are using, for example, epoxy and many polymers have low toughness. So that means we have got two low toughness material. Therefore, the toughness of the composite has to be low. But it is not true, because toughness of a glass fiber epoxy composite is much larger than the toughness of either the fiber or the matrix. So therefore, we can say that this kind of rule of mixtures is not applicable for composites. So we have to use another analysis for this case. So analysis for short fiber composites. So we will do the analysis for short fiber composites, but if the length of the fiber is larger than the critical length, then it is also applicable to long fiber. Now let us see a composite with these short fibers and imagine that there is a crack which is growing, which is here. As the crack experiences or meets the fiber, there will be two things happening. The first thing, fiber pull out, if the length of the fiber is less than the critical length, then the fiber will get pulled out from the matrix, or fiber fracture. If the length of the fiber is greater than the critical length, so if the fiber length is long, so in that case the fiber will fracture. The crack will grow. As the crack grows, there will be two events happening: either fiber pull out if the fiber length is lower than the critical length, or fiber fracture. Now these two events, fiber pull out or fiber fracture, will consume energy. So here we can schematically show this diagram where the fiber is here and the fiber is experiencing a shear between the fiber and the matrix. So as the fiber gets pulled because of the crack growth, there will be shearing action between the fiber and the matrix. And these are the dimensions, and we have taken this length as L by 2 because we assume that another L by 2 is on this side. So now work done in pulling a single fiber out of the matrix by dx distance will be given as. We know that toughness is an energy property, how much energy is being absorbed by the material for unit crack length. The work done is energy. So how much work we are doing, so that work done will become the energy. So in the case of composite, the work done in pulling the fiber out, or fiber pull out, or fiber fracture is much larger than the new surface area created, the surface energy associated with the new surface area. Therefore, we can only talk about the work done in pulling a single fiber as far as composites are concerned. So this equation is given as here. So force multiplied by dx. So we are applying a force, and dx is the distance that this fiber has moved. So this will be the work done, and the limits are 0 to L by 2. This will be equal to pi d. Pi d is the circumference of this cylindrical fiber multiplied by tau fm. Tau fm is the interfacial shear stress between fiber and the matrix. So this is the shear stress between the fiber and the matrix multiplied by x. So actually pi d multiplied by x is the total surface area multiplied by tau fm, it becomes force. So this is the force multiplied by dx, distance. So this is the work done. So this will be equal to pi d tau fm L square over 8. So this is the integration of x dx. So equation 4.55 gives us work done in pulling a single fiber out of the matrix by L over 2 distance. So for the whole distance L over 2. So this is the equation. Now if we assume that the volume fraction of fiber is same as the area fraction, generally this is quite a valid assumption that whatever volume fraction of the fiber we have in the composite at any surface, the area fraction is also same. So we will take this assumption. So now number of fibers per unit area of a crack. So as the crack is being created, how many fibers per unit area of the crack are we experiencing? So this will be given by this one. So imagine we have got per unit area of the crack. So this is the area fraction multiplied by unit single. That gives us the area of the fiber. So total area of the fiber covered in the crack, in a unit crack area. Because AF is a number, a fraction less than 1, multiplied by the area of the crack, unit area of the crack, divided by pi d square over 4. So this is the cross-sectional area of a single fiber. So this gives us the number of fibers per unit crack area. This can be given as this one because just now we said that area fraction is taken as the volume fraction. So here we should know that the volume fraction multiplied by unit area here divided by pi d square. So 4 VF over pi d square will be the number of fibers per unit area of a crack. So we have just now calculated in the previous equation amount of energy spent or work done in pulling one single fiber. So toughness will be given as the work done in pulling one fiber multiplied by the total number of fibers in a unit crack area. So this is the total energy spent or the work done in growing the crack by unit area. And one unit area of the crack has got these many fibers. So we have to multiply the work done for single fiber multiplied by the number of fiber. So this gives us the total energy in creating a single unit area of a crack, and therefore this is the definition of toughness. So therefore we can say toughness is equal to this equation, which will be equal to Vf tau Fm L square over 2D. So this is the equation for toughness of a composite. Now equation 4.57 is derived assuming that the length of the fiber is less than the critical length of LC. So we assume that the length of the fiber is smaller than LC. If the length of the fiber is greater than the critical length, then the fiber will break before enough stress is created for a fiber pullout. So if the fiber length is less than LC, then enough stress will be there that the fiber will be pulled out of the matrix. But if the fiber length is more than LC, so in that case the stress will be high enough that the fiber will break before it gets pulled out. Thus substituting L is equal to LT and using equation 4.48 we can rewrite equation 4.57 as, so here 4.48 we had derived in a previous video sigma F is equal to 2 tau y LT over D. So we will use this equation and we will write toughness as equal to this equation where L is replaced by LT and then LT is replaced by D sigma F over 2 tau y. So here sigma F D over 2 tau y squared, here square. So finally this is the equation for toughness of a composite which has got long fiber length is longer than the critical length. So the same equation can be utilized for short fiber or for long fiber as long as the fiber length is longer than the critical length. Now equation 4.58, which is this one, says that for higher toughness, in order to have high toughness, we should use stronger fiber. That means sigma F should be high with weaker fiber matrix bond strength. So tau y, which is the shear strength of between the fiber and the matrix, so this should be lower. So if this is the lower value, then GC will be high. So this is the condition how we can create a composite which is tougher. However, this condition will lead to weaker composite because we are reducing the bonding strength or the shear strength between the fiber and the matrix. But here we have to compromise. If we increase the bonding strength between the fiber and the matrix to very high value, even though the strength will increase, but the toughness will decrease. So therefore a good optimization between strength and toughness is necessary. So we can see that how the crack will grow in a composite material. So as the crack meets a fiber, the crack actually initiates fiber pullout. So we can understand that the crack will initiate fiber pullout by diverting the crack towards the fiber length. This crack will divert towards the fiber length, and at some point either the fiber pullout will happen or the fiber will fracture, and in that case the crack will further advance. So this crack will meet many fibers along the way, and this is the energy consuming process, and this is the reason why composite is very tough material, even though the fiber and the matrix both may be brittle in nature. In order to have a good toughness, as we can see from this equation, that we should have lower bonding strength between the fiber and the matrix. So this optimization between the strength and toughness is necessary for every composite material. Here we have got some data on toughness and fracture toughness. So just now we have seen the toughness of a material, what is toughness and what is fracture toughness. Toughness has got unit of kilojoule per meter square. Fracture toughness has got unit of megapascal meter to the power half, or we can also write in this format meganewton per meter 3/2. So you can see that for pure ductile metals, toughness is very, very high. Fracture toughness is also high. As we increase the strength of the steel, so for example rotor steels, pressure vessel steel, high strength steel, we can see that toughness is going down. So in this bulk material, which is not a composite, as we increase the strength, toughness goes down, fracture toughness is also lower. For cast iron, which is considered as a brittle material, toughness is very, very low compared to these metals, ductile metals. Fracture toughness is also low value. For all the polymers, polystyrene, polycarbonate, we can see that toughness and fracture toughness tend to be in the lower side. Then this is cermet, cobalt tungsten carbide material. So this is a composite material, and this also has got toughness which is lower because it is a ceramic based composite material with very high strength. PMMA is considered as brittle material at normal temperature. Epoxy is also brittle. Then we have got glass and porcelain, which are very brittle material, and therefore we can see that toughness has gone down by one order, and fracture toughness is also very low. Similarly, ice also has got very low toughness and very low fracture toughness. Now we can see that for GFRP, which is glass fiber reinforced plastic, has got toughness in the range of 10 to 100, fracture toughness from 20 to 60. So this is a range of values, and you can see that these values are much larger than the epoxy or even the glass, for example, here. So we can see that 10 or 100 times increase in the toughness, and similar kind of increase in the fracture toughness when we make a composite out of glass fiber and epoxy. Now I would like to summarize briefly. Toughness of a material is the amount of energy the material absorbs for the creation of a unit new crack area. For a fiber composite, the energy in fracturing or breaking the composite is mostly consumed by two events: fiber pull-out and fiber fracture. These energies are much larger than the energy of the new crack surface area created. The composite toughness analysis says that a composite will be tougher if the fracture strength of the fiber is high and if the interfacial shear strength between the fiber and the matrix is low. Composite fracture mechanism consists of crack growth and multiple crack diversions in the direction of the fiber length during fiber pullout and fiber fracture. This process is an energy consuming one, and this is the reason for very high toughness of composites, even though the fiber and the matrix both may be of brittle type. Thanks for watching this video. If you have any question or comment, please write them down below in the comment section.